Hi, everyone. Again, we have Dr. Jeffrey Blume visiting from the School of Data Science. I'm going to read his bio. It's really interesting. And Jeffrey, thank you for visiting us. It's really a great opportunity for us to learn, to strengthen communication and collaboration with different parts of the school and our institution. So Dr. Blume is a professor of data science. He's also the Associate Dean of Academic Affairs here at the School of Data Science. By training, he's a biostatistician. He's known for developing livelihood-based methods to measure statistical evidence and for inventing what he kind of addressed this morning, which is the second generation p-value, which is a framework to improve statistical inference and reproducibility. His research covers prediction modeling, mediation analysis, ROT methods, and clinical trial design, especially in diagnostic and imaging studies. He has led multiple efforts on numerous large-scale clinical trials, and he actually co-leads the NCI-funded study on disparities in lung cancer screening, which was also recognized with the Vanderbilt Chancellor's Award for Research. Dr. Blume has served for over a decade with RSNA. He has led the clinical trials methodology workshop that they offer annually, being a co-leader in that workshop for more than 5 years. His collaboration spans across radiology, nephrology, women's health, and neuroscience, so very connected to healthcare and what we do. He's also the director of the PRINCE Lab, and that stands for Prediction, Inference, and Scale Data Science models. And he mentors PhD students developing new statistical tools that connect methodology with biomedical applications. Lots of awards and recognition, not only locally, but nationally. So it's really a pleasure to be here for us to host you and for you to get to we get to learn from you. So thank you for being here.
Thank you. Thank you. Thank you for the nice introduction. I'll try to live up to it. This should be a little easier. I had to do statistics at 7 in the morning this morning, which was rougher. So this should be a little bit easier. It's a pleasure to be here. I have done quite a bit in the radiology space. And one thing that I've always thought about radiologists is they're really poised to understand a lot of what's going on with large language models and prediction in this space, if only because they understand what a diagnostic test is really well and how to use it. And at the end of the day, that's what these things are. So one of the things I wanted to do was give you a little bit of a different talk. So I could have come and talked a little bit about second generation p-values. I do a lot of lung cancer screening. That would have been interesting. But all the hype is large language models now, prediction models. And I do have a talk where sort of every bad example of a large language model, reasoning poorly or funny. But the questions I get at the end of the day is, why do these things happen? And how do I know when I can rely on the answer that's coming out of this thing? So what I'm going to try and do is approach things a little bit differently and explain to you some of the inner workings of these things, but all visually. So we're not going to do equations or formulas, but to give you some intuitions about why things go wrong and why you may have some hallucinations, and then try and stack it, build it all together back at the end a little bit, and talk in a little bit more generality about what's going on and show you some examples that I've done and that my graduate student has done looking at the stability of these predictions that you get out of the models. And we're going to do it in simple cases because when you make predictions in text, for example, it's very hard to understand, well, what's the right answer to a text question, right? But there are lots of ways to express the right answer in text. So we're going to talk everything about basically in risk score space so that we can understand sort of what's going on. Hopefully there's some intuition there. So that's the goal. Feel free to raise your hand, ask questions, throw food. That's fine too. I'm good at as we'll go along. As long as you don't mind, I may throw it back. So where to start? So good acknowledgement. So I did use ChatGPT to help with this talk a little bit. The internet, I think, doesn't always get acknowledged, but if we're going to acknowledge ChatGPT and the internet, they're almost the same thing. Lots of discussions with colleagues about how to talk about some of these ideas. And what I think is a pretty good cartoon for today, for those of you, I like the XKCD cartoons. This one's great. So the person who's over here says, well, so this is your machine learning system, right? And the person says, yep, you pour the data into this big pile of linear algebra, and then you collect your answers on the other side. And what if the answers are wrong? Well, you just keep stirring. And so what I love about this cartoon is this is exactly how large language models work. In fact, you pour all your data into something, you massage your data, or we'll talk a little bit about where we put it. We put the data in a particular space, you analyze the data in that space, and then you pull it back out. The analysis that you do in that space is a lot of linear algebra, actually, a lot of cosine similarity, all sorts of things that you're doing. So you're doing exactly that. And in fact, there are papers upon papers saying, hey, if you're not getting the right answer, just keep averaging. Just keep moving things around in your large language model. So this seems to be state of the art. What's amazing is that this can be state of the art, and the tool can be so helpful and insightful for certain things, and also give you crazy answers at the same time. And so I think a lot of this is not just, ooh, we just need to tune this to get it right, but to understand, you know, how these things work, what the stability is, and things like that. So I had to pick some big themes for learning objectives. And I think one big theme is this dichotomy between prediction and inference. We're going to talk about this. These are two different goals. And a lot of folks think, oh, I can be efficient. I can build a model and do some prediction and do inference from the model. That worked well in 1970. That doesn't work that way anymore. I think we want to talk about the big concept, big thing that makes machine learning work, and that's overparameterization. If you have a problem fitting your data, you need more parameters. And in fact, if you can get 100 or 1,000 times more parameters than data, you're good to go, right? And so if you ever remember back to your first stat class where someone showed you a linear regression, they said, look, if I have a point, I can fit lots of lines through that point, right? And so you need at least another point to understand what really that line is, right? Well, machine learning as linear regression was 1 point. That is the direct analogy, okay? And people choose a particular solution depending on how it generalizes, how do your out of sample error, or how you regularize or do various things. And because of that, there are lots of solutions for every given data set. That leads to a lot of problems, and one of them is the hallucination type things that we see. All right. All right. And the last is, okay, so I know how things can go wrong. So then what do I want to do when I have a tool at the end of the day? And I spent a lot of time thinking about this. Where I sort of ended up with is that things, you have to treat these basically like diagnostic tests. They're not magic. That means they need to be treated in the same way you would treat a diagnostic test in terms of evaluating the rigor in which it's built, where the data comes from, what the pipeline flow, what the clinical flow is, how it validates, and what its operational characteristics are at the end of the day. And you just can't get away from doing that. The hard part is going to be that every time you fit a model, you're going to get a different tool. So this idea that I can fit a regression and use it and go on and just use that one thing from now kind of falls away. All right. So we're going to try and understand what their machines are doing so you have some proper context for using them. So let's just start with what the goal is. So prediction is all the rage. I remember when I went to graduate school in statistics, they said, hey, you're going to do inference. You're going to learn how things work. You might even be able to predict a few things, but our models generally don't predict well. And in fact, the economics used to be that if you could find a data set where you could fit a regression and that R squared was 0.4, that got you a Nobel Prize, right? And so now you can get an R squared of 1 minute in pretty much anything, right? All right, so some things have changed. So, but prediction is a very important part of the tool set. So you want to accurately forecast unseen outcomes, right? This is going to now be driven by patterns, but not necessarily by understanding mechanisms, right? So 30 years ago it was, let's understand the mechanism and let's use that to predict. That is falling away now, okay? Now let's just use whatever patterns we can to get accurate predictions. Okay. You evaluate these things by how they perform. This is why having an out-of-sample validation set is so important, because you juice your predictions in the data that you have, and you hope it performs well outside of it. So the typical tools for this are regression or random forest. We have ensemble methods now and neural networks. These things will generate pretty good predictors. And you can do fancy regressions so that they're competitive with those fancier methods. All right. So you might do, say, predicting heart attack from EHR data and imaging data. Inference is more about why it happens. Okay. So inference is understanding the relationships and mechanisms between your predictors and your outcomes, right? And sometimes people say predictors, some people say covariates, some people want to sound fancy, they'll say features. These are all the same things, okay? You want to understand how that happens, and you want to be able to interpret the effect, right? As age goes up, does your risk go up? Does it go up and come down? What happens? Right? And you'd like to maybe make a scientific hypothesis about that effect and estimate it and test it, which all seem like very, very reasonable things if your model is interpretable and you have parameters that you can understand. Okay. And so you evaluate inference by, you look at effect estimates, confidence intervals, p-values, posterior probabilities, all sorts of things. And again, you also have traditional tools, regression, likelihood methods, do causal inference type methods and various things like this. So when I went to school, you tried to do both things with one model. Now we don't do that anymore. So we have a model that will give you high predictions. You'll have a model that you will try and learn from. These models that tend to be robust about particular hypothesis tests, like I'm going to test this hypothesis in this model. What happens if I leave age out and age is important? We would learn about putting the right things in the model and getting a robust answer so that even if your model's wrong, your conclusion wasn't wrong, that's all important here. That model generally doesn't predict very well. And in fact, you can show that you can always find a model that's the wrong model that will predict better than the true model. So you've got this odd thing going on. What's the explosion has been here in the prediction model. And then people are spending their entire career trying to interpret these to do this in here. I'm going to argue you can never do that, but that's called explainable AI. We'll talk a little bit about why you can or can't do that as we go through. All right. So it's very hard to do with a single model. Most prediction models are black box methods, and black box is a good way to think about them. They have more parameters than data, which means there's lots of ways that they could be fit, right? So there's lots of solutions, okay? That flexibility enables fit and high predictive performance, but it leads to overfitting, and overfitting can hurt you in a number of different ways. The traditional way you think is, ooh, my performance I see here is not the performance that I'll see here, which is a natural way to think of overfitting. But that overfitting also means that you can no longer interpret the coefficients as you might strictly with what you have. All right. The paradox here, I think, of modern machine learning is that predictions are massively overparameterized. I'm not talking about a few extra parameters. I'm talking millions of extra parameters. They tend to generalize really well. So all of a sudden you think, well, if I overfit, it's going to get worse. And if I overfit more, it's going to get worse. And if I overfit even more, it's going to get worse. Well, someone just decided, yeah, let's overfit it some more. And they did more and more and more. And then what they find is that there is at some point in which the prediction gets better out here, and then better, and then better, and then will outperform where you started. And I don't think it's not necessarily well understood in a theoretical sense. I'm going to try and give you some intuition for why that happens, actually. But it's not a well understood, and there are things like that are called double descent and various flavors of this that people are spending their careers trying to understand. All right, but that overparameterization means I got a bazillion parameters. So now how do I interpret the coefficient for age if I've got a million other parameters? I mean, what is that? And in fact, the effect of age may be captured in all sorts of other parameters too. I may have square terms and cube terms. So then your ability to interpret that thing falls apart. Also, there are tools, there's something called regularization, which I'll show you an example of, which says if you've got a lot of parameters, you can penalize your model for having too many parameters. So it encourages it to be small. And what that does is it smashes the information down to a few pathways. So you can think of it as the old model, you might have a direct effect and you might have an indirect effect through an intermediary variable. The regularization allows you to drop that extra variable and shove all that extra information back through the system in the direct effect. So you get a juice direct effect. So you lose the ability to interpret. All right. So that's the fundamental trade-off, which is as models become more flexible, it becomes easier to capture complex problems, and you achieve strong predictive accuracy. But the flexibility comes at the cost of interpretability. So the model's internal parameters no longer correspond to causal or mechanistic relationships. All right. And if you want to do inference, turns out that you need structure and you need some constraints. And being able to be good at prediction thrives on complexity and fit. So the models start to go like this. What's a good model for inference and a good model for prediction start to separate. All right. So you got a little bit of a Faustian bargain here. Overparameterized models are very flexible. They can yield excellent predictions. However, it comes at the expense of interpretability. The overparameterized algorithms also are not stable. So what's in your black box actually changes. So I'll have an example of this, but when you fit your model, you estimate all the parameters and you get a set of predictions. It turns out what becomes stable is the set of predictions, not the insides of the model. So if you refit that model, even with the same data, and I'm going to show you some examples of this, you get a different insides of the model, but the predictions are the same. One way to think about why this is if you have a data set with 1,000 folks and you have a model with, say, 1 million features, you go to this giant space, there are lots of ways to predict 1,000 things with 1 million things, right? So there are lots of solutions that will give you the same 1,000 predictions. So that inside doesn't really mean anything. What means something is the predictions at the end. And so that opens up a lot of other things. So false models can also have higher predictive accuracy than the true model. An accurate prediction doesn't imply accurate inference, okay, which is important. And accurate inference doesn't imply accurate prediction. So now when you're using these tools, you really need to think about both things. Yes?
When you say false models and true models, what does that mean exactly?
So that's a good question. You can imagine, let's say there's a linear relationship between age and, I don't know, risk of lung cancer. Okay? And so you want to be able to understand that particular model. And then I'm adding in what I had for dinner. I'm adding in what I happened to read that night on the web. I might add in my medical history, which could be relevant too, right? But I basically have a model that's too big. I got too much stuff in there. That model can predict better than if you knew the mechanism by which I'm going to generate lung cancer, is the idea. So there is some true mechanistic process. It is random at some core point. And by expanding the model to be ginormous, you leverage lots of little multicollinearities here or there, and you make it appear like you can predict better.
So that true model is the actual
Data generating mechanism.
What's the generating? The false is all the extraneous stuff that appears to be predicting.
That's right. And so it's much easier to just fit the big model. And the hope, at least the old school inference approach, was if you fit a model that's too big, you can still learn about the components because adding extra doesn't hurt. That works up until you have as much data, as many parameters as you have data. Once you have more parameters than data, all bets are off. All right. So what I said in words sounds great in words. It looks even better in equations, but I'd like you to pay attention to me for the rest of the talk. So I thought I would try pictures to give you some intuition about what's going on here. So I generated some data, and I picked a Very simple case so that you can sort of see the behavior that goes on in multiple dimensions. And so I made up a response and I have whatever today's favorite predictor is, okay? All right, and you can see the relationship here. I generated about 100 observations. Those are those gray dots. And there is some true model, none of which these lines are the true model. But there's a cubic relationship between here and some flattening at the edges. Okay. All right. So what would the first thing that I would fit? Well, you know, if we were in Stat 101, we'd fit this blue line and you'd have to get to Stat 102 to do anything else, right? It's a problem with statistical education a little bit there. Some stat jokes are okay. Not too many. Okay. So that's that blue line, right? And it misses here. Misses here. It's not too bad through here. Okay, well, what happens, I can make my regression fancier, right? I can capture the non-linearity in this, what we say in this feature space. And I can do that by, I can add an x squared term or an x cubed term. Here, an x squared term is not going to help because I'll get a parabola, but I can add an x cubed term. So that's what that red line is. And it's a slightly fancier x cubed term. You don't have to worry about the fancy, but it keeps the ends from curling up. So they go off in a straight line. It's called a cubic spline. They're the rage now, and they're actually what ends up being the basis of a lot of these language models. Okay, this is ends up what they're getting close to predicting. And then I fit something that's not a model. What I did was I took the data and I just averaged it. I moved a window over, a small window, and I averaged those data. I moved over a little bit and averaged those data, and I go slowly across the whole thing. My computer cranks and cranks and cranks, and I get a nice, smooth, non-parametric line. It's a very reasonable line. It fits the data really well, but there's no formula for how I get from here to here. You could have a lookup table, right? Like I could say, ooh, I'm at number 1. I can go up to orange and come over. That's a lookup table. But there's hard for me to say what the overall relationship is, and there's no way to really do inference. How does X connect to Y? Well, I don't know. It's kind of squiggly, and I got to use my table, right? Okay, this is very close to like a non-parametric smoother, okay? And this is going to be important for understanding what we approximate. These are the two things that your large machine learners end up approximating at the end of the day. But to get there, they have to do worse before they do better. Yes?
So by definition, are all machine learning models false models?
Depends on what you think the true state of the world is. Because usually everyone puts every feature in those things.
They're by definition over parameterized, right?
That's by definition, the goal is to overparameterize, which squeezes
makes them false
out. They're juicing the predictive accuracy. And so when you juice the predictive accuracy, you can't learn. Like here, this has okay predictive accuracy actually, but I can't learn. I can't learn about this relationship because there's no concise mathematical relationship to learn about. It's just a smooth line, right? So I may prefer this because there's a close relationship.
You can't extrapolate that either, can you?
No, that's another excellent point. I don't know how to extrapolate what goes on here because the lookup table ends. Here I can extrapolate. We're going to find out though that sometimes extrapolating even within the data can be problematic. Okay, and why this is important? Because this is the inside of a large language model, actually. Yes.
But aren't there are Bayesian techniques to take each box and predict the next box and to use the box next to it to inform it?
There are Bayesian techniques for everything. I'm not a big Bayesian. But the nice thing about Bayesian is all you got to do is add whatever data you're missing and use that as if it were real data and make a prediction.
So you could extend the lines and use the Bayesian model.
You could,
Yeah.
you could. I think the thing about the non-parametric pieces are you need some parametric model to go beyond the data.
Yeah.
And that Bayesian piece would be that.
Yeah.
Yep. Yeah. Okay. So I did probably something simple, which is I said, well, okay, instead of just going up to degree 3, what about degree 20? Let's get a sense of what's happening. So I fit 2 polynomials of degree 20. So I have an x squared, an x cubed, an x4, x5, x6, x7, 8, 9, all the way up to 20. Now, these are harder to fit because they end up to be highly correlated. So sometimes the model can fit them and sometimes they can't. So I tried two different ways to get it to fit different polynomials. So you can see they're much more responsive to the data, whether that's good or bad is another piece. But you can go way off the tracks here. Okay? But we're still not to machine learning yet, right? I mean, this is only 20. Machine learning's like what? Like 1,000. I got 100 data points. How about 1,000? Well, what does that look like? Okay. So I did that. So I fit some models with degrees of freedom of 1,000. And then I used my regularization technique to pull the model in a little bit, to give it a little stability. And then I haven't drawn the continuous piece on purpose. I just asked the model to give me the predictions for the existing data. So this is the in-sample accuracy of your machine learner. Let's take the green. One thing you'll notice about the green is that all the gray dots are circled by a green. That model with 1,000 degrees of freedom, right, up to 1,000, it does really well at predicting your data perfectly. Your R squared is 1 there, right? No in-sample mistakes. The pink is regularized. Usually that, and one way to think about that is pulling everybody towards the grand mean. So you can see that there's this shift here towards the grand mean. And then I can look up my lookup table, and you can see the lookup table is not bad, but does miss. The key thing that I haven't drawn is what does this look like for this model that fits perfectly? What's the problem? It looks like it does perfectly. The problem is you don't know how it does on data that are not here, right? So if I have this point and this point, I need to predict for a point here for which I didn't actually have a data point, right? So I'm going to connect all these dots. What do you think it's going to look like?
Noise.
Well, it'll look noisy, but it's got to go from one dot to the next dot as you go here. Anyone want to take a guess? It's going to be much worse than you can guess. That's a help. Most people are like, well, I'll just get a straight line.
Yeah.
Right? Except because you have a natural spline, everything's got to be continuous. So if you're here and you need to get down, you usually go up and down. And then you come up to here because the next one's up here. So you need all your derivatives in the right space. So you're going to overshoot a lot.
That's a lot of overshoot.
Welcome to ChatGPT 4. This is basically what the insides of a lot of machine learners look like. All right. Now I'm going to show you what the regularization does, so you get a sense. But this is why the out-of-sample generalizability is terrible. And what's so interesting is that with 1,000 degrees of freedom, this is terrible. I'm going to make it even bigger, and it's going to get better on its own. And we can talk about why it is. I'm going to draw the pink as well, so you can see the thing. See the regularization? That helps a lot. And a lot of that is just by feel. Like there's no rule that, oh, you regularize by this much. This is how much your statistician likes you. This is, whether the computer's in a good mood. I mean, a lot of these are just choices and fiddling with the analysis to try and get that to fit well. But that's a lot better. Okay. And of course, I don't really have that out-of-sample prediction for the lookup table because I don't know how to get from here to here. I could connect with here. I could actually connect if I really wanted to by a line, and that may be the best. And I actually think that ends up the best. All right. So we've done this piece here. Natural spline with 1,000 degrees of freedom is very fancy to all sorts of spline techniques that you would do. I didn't show a random forest. It's not as interesting, but I thought, oh, well, let's do a neural network because neural networks are great. The one I have between my ears is really good. So this has got to work, right? Okay, so this is a neural network where I have 5 nodes and it basically fits a linear regression on every particular node and then does that again for every other node. So I got a lot of parameters here. You can see them. It's like 5 square parameters. Okay. Okay. Well, that's kind of interesting, but I got a Mac, so I can do better than that. Here's a neural network with 20 layers, 20 nodes per, like something ginormous. So this has got way more than 1,000 parameters. It's like 20 to the 20, whatever that is. Okay, so let's take a look at these fits. Here they are. So what's really interesting about this is the ginormous model, which is the blue one, it's really starting to get these big misses under control, but still not very good. And the smaller model is actually, I think, probably doing better. Okay, there's some oddities here. Like, look at that. That's just weird. But it needed to turn the derivative around and didn't have enough parameters to turn the derivative around. So it's flipping it around. What do you think that red line, if I were to take this blue line and regularize it, I'd get a smooth version of the red line. And that's why I left the orange line up there, because that simple lookup table, that non-parametric thing is exactly what the machine learners end up approaching. They end up with some sort of spline approximation of a non-parametric smoother. And all the non-parametric smoother is it takes everyone who's just like you and averages their response. That's it. We're not doing anything fancy. But when I have millions and millions and billions of pieces of data, it's very hard to have a lookup table that I can do this. So I need some mathematical way to connect all these pieces and points. So what it turns out to be is a very ginormous, large spline that's really approximating probably something simple that you would do if you could do it. And that's the inside. That's when you do that averaging of linear algebra pile of garbage and you just keep turning that thing over and over again. And you're, multiplying matrices together, which is essentially just calculating the correlation between various things. All you're doing is averaging over and over and over again. And that's what's going on here. There is one subtle piece that I'll tell you about as we go through, but this is kind of where you're ending up. And these are your hallucinations, right? This is when you're way out. I haven't connected this to like text or anything else. I'm about to do that. All right. Okay. So what's the temptation here? The temptation is you get this extraordinary predictive accuracy. You can pick up these subtle patterns. You get this high performance creates the illusion of knowledge, but you don't really know what's going on, right? Because all you did is you say, ooh, this person's sick. And I gave them this treatment and they got better. You kind of look like that person, and so do you. And in fact, all you people who look like this person, when I gave you the treatment, 80% of the time you did better. So I think that your risk score is 80%. That's it. It's not because of their age. It's not because of their gender. It's not because their image looks a particular way. It's because on a whole bunch of features, they look very similar. And people are basically, independent replications, and you average them and you can get their response. That's why these things aren't interpretable. The mechanistic connections are not baked in. You're just averaging. It looks like you're doing more because you've got these cubic splines and you've got a little equation. But when those cubic splines get so big and you regularize them, you just end up approximating what that local average will be. Okay. So what do we have? So, there are lots of different AI models. You have these diagnostic models where you're trying to detect diseases. You've got forecasting models, these predictive models. I saw this is kind of a cheesy, I don't know if you saw this last year, AI defeated doctors, I mean, that's great for subscription rates, but not very healthy for science, right? And you could really pick at what's going on there. They have now prescriptive models, recommended treatments, right? Anyone using Watson for their treatment plans? No one? I don't know. At some point, I had heard that this went defunct and then came back. So so that didn't work out so well, right? How come? It's because the mechanistic interpretations are important. It's just because people look together doesn't mean that everything's going to happen the same. That's not the science. That's not the medicine, right? All right. And you've got now a lot of these monitoring models. They're all over your phone. They want to collect all your data and tell you, what's going to happen later. Okay, so I wanted to just connect with you in the language about where what we talked about fits in. So what's a foundation model? So a foundation model is a large pre-trained model designed for general purpose tasks across various domains. And it requires large, diverse data sets for pre-training. It's got high generalizability, but it's not very specific. Basically, it's the entire internet in a model, right? Okay. All right. And then you have what I think of, what we traditionally think of as a disease model. So you're trying to address a specific condition. You have a lot more limited data. You might be looking for a mechanistic interpretation. So you've got these pieces. And the components of AI is basically a foundation model and now a language model. So if I was giving this talk to maybe 2 years, a year and a half now, we wouldn't be talking about the language models, right? That's the new piece. And that's because it made everything accessible. Okay, and now language models are starting to replace the disease models. And I think you definitely don't want to do that. And I'll explain to you how that's happening now. So the foundation models are large pre-trained models. You learn from diverse data. You can put in text, images, all sorts of things. It's adaptable to many medical tasks. You've got like ResNet, MedPalm, you got all sorts of things. I don't know how many people are using these things or not. And then your language model has a very specific piece. It's a type of foundation model for understanding text. And really all it does is it takes text or unstructured data and it puts it into a space that you can understand what it is. Because in that space, you want an average. Okay? And I have reasoning here in quotes. Because the averaging that goes on in that space is what people think of as reasoning. It's not actually logical. All right, let me see if I can. So here's basically how it is. For the large language models, you get a data input, text, images, audio, graphs, they're broken down. So if I have a sentence, I would break that sentence down into the set of individual words. I would also break it down into the set of 2 words, 2 consecutive words. I would break it down to the set of 3 consecutive words and 4 consecutive words. I would then break it down into the set of the first 5 characters, the first 6 characters, the first 7 characters, the next 5 characters, the next 6. So I would basically chop that up in all the ways it can. And each one of those pieces is called an embedding. Okay? And what the model does is it takes that sentence broken down in all those ways and it maps it to an embedding space. And then when it looks at another sentence, it says, ooh, these 2 words are together and the first 7 characters are the same. So that embedding space is going to goes close to this embedding. And then when you want a prediction, it looks around that embedding space and says, oh, you're here. Let's average everything here and spit it out. And then it reconstructs the language. Okay? So the models really are just mapping data into points in high dimensional space. And you're doing all your analysis in high dimensional space you should be doing it the way I showed. It's not quite as sophisticated. The computation gets performed in that embedding space. You average, you decompose, you transform, you do all your similarity suggestions. That's all happening in a fancy space. That's why it's worked. Basically, somebody took your regression and they found the nicest set of transformations of your covariates that were most predictive, and they run a regression. And then they translate it back to your original covariate space. That's what a large language model does, simply. That's it. It's just searching for the space in which your variables can be most predictive. And then it decodes them and it gives the answer. So reasoning is nothing more than manipulating geometric relationships. You're just averaging. You're averaging everything. Here's what an embedding space looks like. I pulled this off Hugging Space. So this is the embedding atlas of 50 random words and their closest tokens. And so basically, this is from DeepSeek, and they said, okay, what sort of information do I have in my corpus? What are these 50 words and how are they related? And you can go here and you can scroll over this and it will tell you what all these words are, and it will tell you what similar tokens are. And so if someone says, oh, I was looking, up in the sky with my flashlight, you may end up here. And you want to know how bright it is, it's going to average all this information here to figure out how bright it is and send it back. So that's all you're doing is finding the right feature space to do a lot of these things. This is not reasoning. It doesn't go through and it says, gee, what's a synonym, for sky? And it doesn't do any of that. Doesn't think, can't add, doesn't put sentences together correctly. It just knows that other sentences are structured this way. So when it spits things out, it structures them in the same way. And the way it does it is it finds an example that's just like the inputs you have and takes its response and spits it back out. And by the way, it's super helpful. I mean, it'll edit papers, it'll give all sorts of information. It works great. It just doesn't know what it's doing. Okay. So the way the large language models, basically they do everything in that embedding space. The trick is that space that I showed you has to be learned from the data. So someone doesn't sit down and say, okay, you're going to be in 1,000 unit space. And this, you get 5% of this vector and 6% of this. When it's averaging, it's learning the best space that will allow it to go back and predict the observations it has. And that's the machine learning part of it that makes it so complicated.
That's all from training.
That's all in the training piece. So the training, the machine learning, the model learns how to map into a meaningful embedding space. There's lots of embedding spaces, but it's picking one so that when it decodes, it tends to end up at the right place. That's all it's doing. And it's basically doing it by trial and error. Okay? This happens inside the large language model. This is traditionally machine learning. If you do a principal components analysis and you fit a random forest and do something, you're doing the exact same thing, except your principal components analysis can't read a note, a clinical note. So what the large language model has the advantage of is it can translate all those notes, all those words and letters into some points in the embedding space, go do all the stuff in the embedding space, which is too big to look at anyhow. And then it does some sort of optimization, which is often suboptimal, and then we'll spit things back out. And there's a lot of work now of people, for example, we have one of our faculty in data science who said people were using large language models to do time series predictions. So he went and took a large language model and stripped out the language part and said, how predictive is it? Turns out it's terrible. You're much better with just a plain old time series model. It's easier because you just dump it all into one place and it does it, but it's nowhere near as accurate as it should be. All right. All right. So let's see. I do have a couple more examples. So these are fantastic tools for mapping complex data, text and images. The machine learning or reasoning parts of these models can be improved upon, and they work because they overfit and because they have more parameters than data. Okay. So what happens inside the box? This is how I want you to think about machine learners, right? So here's the data. Doesn't matter what the data looks like, and you want to get to predictions. If your data is images and you want to be multimodal and combine it with notes, that's still data. We're going to take that data and we're going to mash it up and we're going to fit at some mapping from your data to an embedding space and back to here. So what do you need to know to be a good clinician? My claim is you don't need to know anything that's going on in there. All you need are the predictions, right? Well, if you're doing a diagnostic test, that's all you need, right? You get people's score. You take the people who are diseased, not diseased, and you and plot their two histograms together, right? So here's Schrodinger, he wants to know where his cat is. I don't actually know where his cat is, but what happens in here is not well understood at all. A, B, it's not reproducible. If I fit a model, even with the same data, and then the next day I fit it, I don't get the same black box insides. I do tend to get the same predictions, but not the same. Not the exact same. That's the last piece that I'm going to show you. And so the stability can be an issue. All right. So we know how to do this. We know we can evaluate the black box by looking at the predictions, and it's nothing but like an ROC analysis. And here is how one looks. Here, what I did is I generated risk scores from a multimodal lung cancer nodule detection algorithm that uses CT screening image, demographic variables, and clinical data from the EHR. And there were roughly 1,000 cases and 5,000 cases. I juiced this a little bit and smoothed them so they would be nice. These are people with no disease and these are people with disease. I want to know, is this a good machine learner? Well, what do I do? All I gotta do is plot everyone's risk score, right? This is the training data. So is this a good diagnostic test or not? So ROC curve is 73%. Who votes good?
Yeah, we don't know.
Why don't you know?
Because we only know it for this data set.
Well, okay, so let's suppose that this were to generalize. Is this good or bad? That's fair.
There's a lot of overlap between the.
There's a lot of
cancer.
overlap.
You've got a close to 100% predictive ability for people with no cancer, saying cancer, say high possible.
Yeah, this is pretty sucky, right? Normally you're used to two things where the overlap is here and you draw a cutoff, right? And you move that cutoff, but that doesn't work in this case anymore because the cutoff here will classify these people wrong, right? And if you shift it here, it classifies these people wrong. So this is a case where the model didn't get the feature space right because I stopped it early and it's training. Okay, so what you want at the end of the day are two curves. So this is all you need to look and diagnose in the model. In fact, you can easily fix this. I have two columns of data now, diseased or not diseased and risk score. I just do a logistic regression of risk score on disease and I do risk score squared because I want to capture these people and these people without capturing these people. And you can instantly make this better and you can get your ROC curve up to almost 87%. But the models don't automatically get the feature space right. They got the feature space wrong here. There's something about these people that it didn't get right. Now, I could rerun it and not necessarily get this. I could extend the training and not necessarily get this. But you're not going to be able to do that when you read a paper. And you're not going to be able to tell whether that's happening if you just look at the ROC curve. This is what you need to do to be, I think, to be good physicians. And you should be used to looking at this. So the way you should think about black boxes is they take all that information and they boil it down to one number, a risk score. And at the end of the day, you're using that risk score to compare various groups. And how they do that, super fancy and fun, and you can go get a PhD in it, or you could study in the evening or whatever, or you could blow it off. But this is the consequential piece here at the end. And everyone should be able to understand that and to look for it.
But you're not seeing this very often in papers.
Well, this is why I showed it. You don't see this because people don't know to look for it. But that's exactly what you want to see. You'll see this or you'll see some F1 score. God, if I see an F1 score, I reject. Boom. That's it. F1 score doesn't tell you anything, especially about whether you want to use it. You need to at least know what sensitivity, specificity of an operating point or something, positive, negative predictive value maybe. But all these machine learning metrics assume the prevalence is something, and then when the prevalence is something that kind of approximates something, then you just calculate what they really need. But this is the insightful piece. This is how you check to see if your model is doing what you need. You could be missing an important feature. Like sometimes you load data in and age is in character, not numeric. And so then it doesn't work. You wouldn't know. Okay. I'm going to just show you some examples of actually models that I fit. So this is Gusto data. It's an old data set, 30-day mortality following an acute MI. I got about 40,000 participants, which is why I like it. 29 variables, features, predictors, covariates, almost 3,000 deaths for an overall risk of about 7%. And this has been analyzed a fair amount, and people have been like, okay, here are the 7 most predictive features. Gender, age, hypertension, hypotension, trachycardia, previous MI, and ST elevation on ECG. Okay, pretty kind of makes sense, right? So the first thing that I would do is I'd just run a logistic regression. I mean, I don't need chat fancy. I just run a logistic regression and see what happens. Okay, so we're going to compare sort of what happens now. That's the logistic regression. And what I did was, I know people's truth. This is good, their actual risk. Then I resampled my data. I did something called a bootstrap and fit the model again. So I added a little noise. And if the model's stable, I should, for each person, get their same predicted risk, right? So for this person who's 20%, when I do this over and over again, I get a little bit of variance, maybe 17 to 18%, but that's not too bad. And so you can see it's highly calibrated, right? And the accuracy was about 80%, so that's pretty good, and it's pretty stable. So why not get fancier? Why not? Okay, so let's see. So I then went, I said, okay, let's fit, and I should say, actually, my student then went and said, let's fit a model with interactions. So all possible interactions. Still okay calibrated on average, but what do you notice?
More variance.
More variance. Is that a good thing or a bad thing?
So if you want to pinpoint us.
So if you're a patient now, and your true estimate is 20%, you could get anywhere between 10 and 21% now. I don't know if that's a good thing. Now, if this line were off center and not calibrated very well, and this is more calibrated, I might be willing to accept some more variance to be accurate, but that's not the case here. But why stop here? I mean, I'm in a data science school. We could be even fancier. So here you go. Here are all six-way interactions. What's happening to your predictions as your model gets more and more overfed? The variability is going crazy. This is a person. This is a person. This person had 2% risk before, and now they have 95% or 90% risk of an MI. That's not good. The model's breaking down, and we're not even close to ChatGPT proportions yet. Okay? So this is what happens, and I think you don't see this at all in the literature. This is what my student and I are working on, and this is a really, really important piece, and we're calling it sort of the stability of these predictions, which is if you want to use these in clinical practice, you need to have some reliability if you're fitting the model over and over again. This is the variance of your risk score, basically. It can't be that the variance of your risk score is plus or minus a half. It's not a useful tool. So here we did with only 500, so you could see the effect. When you only have 500 observations, you get that variance that you would expect, right? Before I had 40,000 observations. And here it is with 500 observations and six-way interactions, the model is starting to default. Sure, you will get a predicted risk. But the stability is a problem. Yes.
As the parameters increase, does that become better, or does it just keep on getting worse and worse?
Well, that's great. You're my plant. So let's take a look at sort of at what happens. In the interest of time, I'm going to skip this. I regularized that. So there are some things that you can do to try and make it better. You can use some regularization. Here's a neural network, by the way. So this is better than the six-way, and it has a lot more parameters. So the structure is better, but I can't interpret. Here, I can tell you what the predictors of risk are. Here, I get a little bit more stable risk estimate, but I can't tell you why. Trade-off. Okay. And then I'm going to do these are my last couple slides, just some trade-off here of, we went and we simulated some data, and then we plotted all the different simulations, the calibration curves here, and we're just running through them so you can see how much variability there is. And so this is a model with 4 parameters. So there's going to be something that you would expect. And that's what that sort of variability is. So what happens if I added a bunch of parameters? Here's a model with 8,500 parameters. It's a big old logistic regression. The logistic regression structure doesn't handle the calibration well. You can see it coming up and coming down here, but you can also see the variability going up. And so this is what we're working on in my lab. Here's a neural network, an overparameterized neural network. You can see a lot of variation. Now, that's not quite the rub. What I'm going to show you next is the rub, but you can get a sense of that variability is captured here. You get quite different calibration curves when you refit these. So more parameters, much, much more sensitive to how you fit the model, what particular data you have, right? Fewer, you get something that's a lot more stable. This is why inference is easier here, not possible here. So this is a large piece of it. All right, what happens if I refit the data over and over again? Same data. Like if you fit a regression over and over again, what happens? You usually get the same answer, right? Okay, so here's my logistic regression. I fit it over and over again. 4 hours, I'm refitting it over and over and over again. I'm getting the same model. What do you think happens with the overparameterized models every time you fit it?
They change.
Yeah, that's exactly right. They change. It's not, in this case, it's not as drastic with the 85, you can see. But I'm not even changing the data, I'm not changing the model. I'm just redoing it. So there's some extra stochastic piece of these overparameterized models that we don't understand very well yet. And again, if you're a patient, you know, if you're jumping around between 0.4 and 0.6, you might not care. If you're jumping around from 0.2 up to 0.2 up to 0.5, yeah, you care. And here's that neural network. Lots of interesting behavior there. So if you think about what we do as data scientists, this is what we try to do, try to understand this behavior. Because the overparameterized models are not going away. It's just too easy to take all your data and to send it all to some embedding space, not have to worry, do I have x squared, do I have x cubed? Should I have these two pairs of words? Or it just does it automatically. But then the downside is you've got all these parameters, right? You can get a high predictor, but there's a lot of instability. And it's there, you just don't see it. The paper comes out and says, look at my accuracy, this is great. You have no idea this is there. When it ends up in Epic, it's there. So this has to get worked out in some way, because this could really, especially if you have a low threshold for screening or something, I mean, this could really blow things out of the water. I also think that one of the reasons that these can be surprising a little bit is people are used to thinking, ooh, my risk score is 0.004, and that's real. We're not used to thinking about the variability around the risk score. And there is actually substantial variability. If you're using some risk score model that someone fit on 500 observations, is pretty big. Okay, I will take questions and I will just go to what I think is the last slide. All models are wrong, but some are useful. Okay, and I'll leave this up here for if there's things that you want to read. If I'm reading stuff, I'm worried about accuracy, calibration, stability. That's the take home. Questions? Yes.
So since we have Colin here, who's our dean of the School of Medicine, what are the perils to medical education when there becomes an over-reliance on these predictive models? Do you think we lose the ability of understanding inference and causality? And if that is going to become the new norm, how do you guard against that?
I don't know. I think it's really a new era in the sense that the ability to predict is so outsized and more advanced than inference. It's just easier to do the prediction than inference. And that gives the impression that you know what's going on. And in order for science to advance, it can't just go prediction for prediction without understanding the mechanistic behaviors there. Also, how are you going to do an intervention? You're highly at risk for whatever. You know, how do you do an intervention if you don't know what the actual risk factors are? It just sort of cuts medicine right off at where we're used to thinking about what our pathway is and how we do preventive care. And so I think what I do in practice is I fit two of these models actually. So I fit a model, and I think everyone should do this. So I didn't put it in here, but I fit the fanciest model I can to figure out how much information I can squeeze in a predictive sense out. And then I fit a mechanistic model and I sort of compare how accurate they are. And so like if I have an AUC of 99%, that's an overparameterized model, and an AUC of 63% with my mechanistic model, then I don't believe whatever is going on in the mechanistic model. It's just too far from the information of the data. I missed something. A lot of times you can go back and get them to be close. So I spend a lot of my time trying to get them to be close. Something that's predictive and stable, and then I get my predictions from the lower predictive, but the mechanistic model that I can understand.
Jeff,
But that's me.
maybe an example to bring that to life. So let's say you've got a model that predicts risk of hypertension, genetics, age, all these things go into that barrel. You come up with a prediction model of people that are vulnerable for developing that or developing a brain aneurysm, whatever. But you don't know the mechanisms, you don't know the intervention. So if that's what you're saying, and then
I mean, you could do watchful waiting,
right?
but usually it's too late for a brain aneurysm, right?
But just the fact that that prediction occurs, that alone allows you to start testing hypotheses. There's value to the prediction, even if you don't know mechanism, right? Or am I missing something?
Well, the question is, I don't know is the answer, which is kind of a cheap answer to your, which I think is a thoughtful question, which is like, how do we take a step forward here?
Yeah.
I can manipulate and squeeze all sorts of information that's correlated into a box and get a good prediction out of it. If I can't recreate that,
Yeah.
Even if it's a complicated model with squared terms and cube terms and interactions, and I can't get anywhere close, then to me, that's a real warning sign that I don't understand what's going on. And I get nervous as a scientist.
So you're worried about the accuracy of the model, or the prediction may not be accurate because you can't recreate it?
Well, the model that I can interpret can approach the accuracy of the fancy model.
Yeah.
And so you could use the fancy model as sort of a process piece, but I don't know how to prevent what's going on. I can tell you it's going to happen, but I don't know why, kind of a situation. And I think the hope or the belief is that you can go back into your data and try and figure out what that is. Sometimes that's possible,
Right.
Sometimes it isn't.
But I guess what I'm saying,
Trying
I
to
don't think it's always necessary, because I think even just having the prediction allows you to come up with some hypotheses for what that might be and test them.
Yeah, so if you do pull out cancer and your surgical margins aren't clean or whatever, and you do your first line chemo or whatever it is, and then you come back and there doesn't look to be anything there, but your model says the person's at risk.
Yeah.
You might do another round.
Right.
You don't need to know why.
Right.
For sure. But that's a decision threshold piece. It doesn't tell you why it will come back.
Yeah,
It could be
right.
genetic history and then you're just getting that through some other pathway.
Yeah.
For which the second line of chemo may not work.
Yeah.
Yeah, sorry.
No, I'm building on Colin's question. Is it recursive to then use the predictive model that has high accuracy, but no ability to gain inference to select the parameters that improve your mechanistic model?
So the answer would be yes, if it were a well-structured problem. So if you had more data than features, the answer is all these things are possible, you can figure it out. But the game is set up so you always have more features than data. And so is it these 3 characters that's predictive? Is it these 4? Is it these 5? It becomes not even a meaningful thing anymore. And so it gets very hard to map that back into a more scientific space that the causes are constrained. Because you've just lumped everything together and you've done crazy things. Images get broken down into voxels and by their RGB color and the nearest voxels, but then they can also pick up relationships with other voxels at the other side. I mean,
Right, and the difference here is that you're not feature engineering anymore. You're not selecting features, right? The model is creating the features.
correct.
And you have no idea what those features mean, so there's
Correct.
no way to back out of that.
That's correct. The famous example was the dermatology machine learner that ended up on Stephen Colbert, where they could predict with almost 100% the slides, whether they were malignant or not. And then he expanded the picture on his show and it had the tag that said cancer. But you can't tell. But it had figured that out. And I think that happens in imaging, right? We know, some machines, a research machine has different prevalence than a regular screening machine, or you'll get only Simon's machines in some place. So it's a patient flow thing. It pulls that stuff out very, very quickly because it can figure it out. We would just dismiss that because we know it's not useful, but it's good for predicting. Well, I don't know if it's good for medicine though. Yeah, great.
My cousin who's older got a PhD in AI in the early 90s. And when I was training in radiology, he said, "Why are you training in this? Machines can already do what you do." And I said, "You don't understand radiology." He said, "You don't understand AI." I'll take my chances. Then Watson Health came out, made this big splash. They're gonna be able to read images. And we went out to their lab, a group in California. We thought this doesn't look like it's really gonna work. And then they kind of died down. And Jeff Hinton said, "We don't need radiologists anymore in 5 years."
Jeff Hinton thinks the
So-
world is ending
so-
tomorrow. Yeah.
You have an amazing longitudinal relationship with radiology and deep knowledge of AI. What are your thoughts on the future for radiologists who are training in radiology at this point?
So that's a great question. So I think there's two things. First of all, radiologists have been doing this since radiomics, like we were talking about. I mean, they've been on the AI bandwagon for a while. The tools will get fancier and it gets harder to understand what's going on, but jobs really aren't going away. What could happen is the process flow could get improved so that images that may not need your immediate attention can, people can check that they're okay, or they can generate a report that's okay. People can come back to those and focus on the harder cases. But to do that, the culture of radiology has to change. Everyone's looking for the abnormality. I think that's the mistake. Everyone's got to look for what's normal and then triage it. And then let the human minds focus on what's abnormal. And the machines are really good for that, but they're really bad distinguishing in a bunch of abnormal things. What's okay, what's a little weird, what needs to be followed, and what's really serious. They're still terrible at that. So I think the future is an AI assistant who could tee things up for you. But I don't see it changing, especially if you ask these things to reason. I mean, you get scary. They really can't reason. They're just averaging things that are like them. You know, you got to remember that, because sometimes it seems like it's reasoning, but it's not. So I don't think the threat to radiology is anywhere near as bad. I think there's a bigger threat to like air traffic controllers and civil engineers who are designing streets and, you know, turning lights on and off and doing all that can get automated much easier with less consequences than medicine. It's also much easier. But looking at these fuzzy images, it's not like the images are clear and there's a big red dot that's flashing, right? You know, the CS folks are great because they're always like, ooh, I took an image and I put a red square in it and I can find the red square. I mean, like, sure, you know, my 10-year-old could find the red square too. I mean, but when they start with the core images, it's much harder. And there's a real learned process that gets tuned that I don't think we're anywhere close to. And that experience doesn't substitute from just running a bunch of highly curated, it can't be achieved by running just through a bunch of highly curated cases. So I don't think it's as doomsday, but I think there's an opportunity for radiologists to be leaders and pull that in as assistants, save yourself some time, charge people extra for it or whatever, and you know, use it. So yes.
So based on what you've said today, is it safe to assume that where we're at now with the algorithms that we have now, we are not going to get away from hallucinations no matter how much data we pour at it?
Yeah. I think that's a nice way of thinking about it. And the problem is because if you look at the models, they just keep trying to build the models bigger. So if you actually look at things like DeepSeek, which claim to have roughly equivalent accuracy, whatever that means, super soft to ChatGPT, that model was like 1/10 of the size, okay? And its hallucinations were less extreme, but it would more often just be totally off base. So a hallucination is like, here's why, blah, 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 blah. If it missed, it would give you the wrong answer. But as the models get smaller, you'll get less and less of those hallucinations because it can't smooth the entire space of embeddings. It's too big. It needs a mathematical formula. And so X to the 1000th might seem like a good idea, but you know, to turn and get to the next point, all those hallucinations are what's happening. You just can't get rid of it until you smooth. There may come a time when the data centers are bigger than Virginia, and yeah, you can just store that lookup table. In that case, the hallucinations will go away. And then you'll just be getting the local average of everyone who's like you in every possible way. But I don't think that happens for 50, 60, 70 years. Yeah.
Long-term question, there have been people who've said that the jump from GPT 3 to 4 and now 4 to 5 has been incremental. You just can't parameterize the world, and that it's already scraped the corpus of human knowledge. Do you believe that that is true, and that we have to look at like abstract model reasoning to get improvements in AI, and that we've hit kind of the speed limit?
I think you've hit a data limit. There's just not a lot of data. And so you can squeeze something else by adding extra dimensions, but you can't really squeeze a lot out of it. And there's, you know, when they spun that up, it was the whole internet, and they generously took everything that they could get their hands on. So they have everything. There's not a lot more to add. So I think the growth will be slower. And I do think they're reaching some of the limits of their engineering capabilities. So they're going to come back and try and improve the models by making them smaller. I think GPT-4 is better than 5. 5 will do very specific things, but 5 also goes way off the rails too often. I think 4 is much more stable. So incremental, but not necessarily incrementally better. Yeah. Okay, I hope that was helpful. I didn't know how else to do it.
Dr. Blume, thank you so much for
Thank you.
meeting that one.
What's that ChatGPT in the bag?
Small time. Small time.
10 parameters.
Yeah, exactly.
Thank you. I appreciate it.
As kind of a nod to our shared history of the academical village at UVA, you can open it now, you can open it later. I don't like opening gifts to everybody, but.
It's a black box.
All right, but thank you very much. Hopefully, continue relationship with the School of Data Science.
Yes, I will put a plug in. We do have a lot of faculty who would like to collaborate. And so for people who have interesting projects and are looking for collaborators, please feel free to reach out to me and let me know. We also have a lot of faculty who think they only need, and UVA in general, they only need the images and they can do everything themselves. And I try to really discourage that as well. Kriya and I were talking about it. We'll send those people to you guys so that they understand the science. But that's the magic sauce, is that mix. So if we can promote that, I think that would be really good. Okay.
Thank you.
All right. Thank you.
Thank you.